Welcome to you all friends. I am Professor Mohammad Tariq in the Department of Economics, AMU Aligarh. In the last lecture, we had talked about the portfolio where an investor invests in a number of assets and the decision by the investor is being calculated on the basis of three factors: the mean return on the assets or the mean return of the portfolio, the variance of the portfolio, and the covariances between different assets. We made a calculation and the mean, the return R W1 R1 plus W2 R2 plus W3 R3 plus WN Rn. This is the weight or the proportion of a particular asset 1, proportion of particular asset 2, proportion of particular asset 3. The mean value of R was the average return on the portfolio. It was being calculated like this: W1 ER1 plus W2 ER2 plus WN ERN, or we can write down like this: W1 R1 bar plus W2 R2 bar plus WN Rn bar. And the variance of R, this was being calculated, expected value of R minus R bar square. This was the variance that we had calculated, and this was equal to Wi Wj sigma Ij. Ij is equal to 1 to, and what do we find this Wi W and sigma Ij? This talks about both variance factor as well as the covariance factor. When I is equal to j, this becomes simply sigma square. So that will be a variance. When I is not equal to j, this will be the covariance between the two assets, how the return on the two assets are correlated. So the decision is being taken by an investor on the basis of mean return, on the basis of the variance, or you can say standard deviation, and on the basis of covariance between the assets. So this is the way in which the decision is being taken: mean, variance, and covariance. And we have also, with the help of the example of a die, we have shown that if two dice are being thrown, the standard deviation or the variability goes down. So from this we can infer that if we diversify the portfolio, if we diversify the assets, the variance will go down, and this reduction in the variance, this reduces the risk factor. The risk factor is being reduced if we have a lower variance. The risk factor is, now it is because of this reason that we say whenever we go and make investment, we should make investment in a number of assets, and we should, in order to make a portfolio, and this we can also call it as the diversification of portfolio. Diversification of this is also called as the diversification of portfolios. So this diversification of portfolio, this is because of this factor, it is being said that uh, we should not try to put all the eggs in a single basket. All the eggs in a single basket should not be put. Let us take a hypothetical example where we assume that the variability of all the assets, it is constant, which is equal to sigma square. The variability of assets, sigma square, with if there are n number of assets, are there. So this n number of assets equally distributed, equally distributed. So what is this? W1 is equal to W2 is equal to Wn, which will be equal to 1 upon n. So this is what we say. Now then, mean return, this can be written as, this is sigma wi ri. What is wi? Or you can say roughly this wi is equal to 1 upon n. So this is 1 upon n sigma r I is equal to 1 to n. This is mean. Now if we talk about the variance of this, variance of r, so this variance of r is equal to expected value of 1 upon n sigma r minus ri minus r bar square. So this we can write down, this is equal to 1 upon n square, I is equal to 1 to n. So 1 upon n square, expected value of ri minus r bar sigma sign whole square. So we can write down this in terms of variance covariance format also. So in that situation, if we say that the assets are correlated also, then this equation will not be simply for the variance, rather for variance as well as covariance. So this I can write it down like by splitting this ri minus r bar I is equal to 1 to n into this is one part and this is another part, sigma rj minus r bar. So j is equal to 1 to n. So n items are here, this square, this has been split into a square is equal to a into a, so this is equal to a into a, but this could be I may be equal to j, I may not be equal to j. If I is equal to j, then we will have variance, and if I is not equal to j, then we will have, or we shall have covariance. So these are the term. In total, when you multiply this, which is from 1 to n, here also this is from 1 to n. So if you multiply these two terms, you will get n square terms. So the number of terms or number of items, this will be equal to n square. So this can further be split into, so this is 1 upon n square. So this can further be split into 1 upon n square into sigma v. If I is equal to j, if I is equal to j, then this can be written as sigma square, the constant variance we are assuming for all the assets. If I is not equal to j, then in that situation we write down like this: sigma square ij. So ij is equal to 1 to n. This can further be split into variance and covariance. If I is equal to j, then this can be written as sigma square plus I is not equal to j. If I is equal to j, if I is not equal to j, then this can be written as sigma I j. Clear? So when I will be equal to j, out of this term n and n, I will be equal to j, and the total term, I told you this will be n square. When you multiply this up to n by n number, so the total number in the summation, if you expand the summation, the total number will be equal to n square, where some of the numbers will be where I is equal to j, and some of the numbers will be where I is not equal to j. Where I is equal to j, that will show the variance. Where I is not equal to j, that will show the covariance. So there are n numbers where I is equal to j. There are n numbers where I is equal to j. And what about the total number? Is total number of terms is n square. So n square minus n numbers will be where I is not equal to j. So if you go and add this, this will be equal to 1 upon n square. Since sigma square is constant, so this is n sigma square plus n square minus n square minus n into this term sigma ij. Now let us take a hypothetical example where we consider that this sigma ij, this is equal to the 0.3 into sigma. Sigma ij is equal to 0.3 into sigma square. Means the assets are correlated like this: sigma ij is equal to 0.3 into sigma square. Variance of R, this can be written as 1 upon n square n sigma square plus 0.3 sigma square into n square minus n. Now this is equal to, this can be written as 1 upon n sigma square plus 0.3 sigma square. You divide this by n square, this will be 1 minus 1 upon n. So this we can write down like this: 1 upon n sigma square one upon n sigma square plus 0.3 sigma square minus 0.3 sigma square by n. So this is equal to 0.7 sigma square by n plus 0.3 into sigma square. This is when we assume that the assets are correlated, or this correlation sigma ij, this is equal to 0.3 into sigma square. So what inference we can draw from here? If we diversify the portfolio, it is inversely related to n, means the number of assets. Inversely related to n, this means number of, it is inversely related to the number of assets, small n. So this variability, or what you may say, that this risk factor, it goes down if we increase the number of assets. So this is one part of this equation. The second part of equation, this is independent of n, 0.3, 0.3, okay, 0.3 sigma square. This is independent of n. So if n is being made quite large, or if n tends to infinity, if it is quite large, then this first part upon this tends to as 0. So despite this, the variance of R, it will be equal to 0.3 sigma square. So what inference we can draw? That if we increase the number of assets in the portfolio, it may not reduce the variability uh, to 0. Rather, the minimum variance will be there, and that is equal to 0.3 sigma square. This is due to the fact that the assets are correlated. So there is a correlation among the assets. So that factor remains here. And it is on the basis of this that when decisions are being made, that a theory was developed by Marco Wies, and he tried to show the relationship between mean rate of return and standard deviation. Mean rate of return and the standard deviation. This relationship he tried to establish, he tried to put. Yeah. So this we can also understand with the help of a diagram in R bar and sigma plane. R bar and sigma plane. So what will be in R bar and sigma plane if we have the different portfolios? So what will be the path of portfolio? How much of asset 1, how much of asset 2, how much of asset 3, or how much of asset 4 will be purchased by the investor? This path we are trying to find out in this R bar and sigma plane. So since graph has this limitation that we can take only two variable on the two axes like this, on this axis we take R bar, on this axis we take sigma. So on R and sigma plane, the path of these assets, we are trying to find out how much of asset 1, how much of asset 2 will be purchased, because here we are simplifying, we are confining ourselves to a case of two assets, and whatsoever is true for two assets will be true for three assets, will be true for n assets as well. So there are two assets we assume, and this the weight of asset 1 w1 is equal to 1 minus alpha, and let this w2 is equal to alpha, such that our assumption that wi is equal to 1 is being fulfilled. Wi is equal to 1 is being fulfilled. So if if alpha is equal to 0, then entire investment in asset 1. If alpha is equal to 1, then entire investment in asset 2. So we have entire investment in asset 1, entire investment in asset 2 in this situation. So what will be the path of the two assets? How much of asset 1 and how much of asset 2 uh, will be purchased? This depends upon the value of alpha, and value of alpha will lie between 0 to 1. So between 0 to 1, the path will be decided by whether alpha is equal to 0.1 or 0.2 or 0.3 or 0.6 or 0.7 or something like that. So this will be decided by this path. So if we try to draw the portfolio diagram, this is some portion is dotted portion. I'm taking the dotted portion daily. This is for short selling where WI becomes negative. So the dotted portion, here let this be considered as 0.1. This is the relationship between R bar and sigma for asset 1. This is for asset 2. Clear? Now the path will be decided between 1 and 2 like this. So here the correlation coefficient is 1. In this case it is -1. In this case this is also -1. Now this is the path. We'll prove this with the help of some simple mathematics, that why this path will be there. This path means if R bar is increasing, sigma is also increasing. This means there is direct proportional relationship between R bar and sigma, and that proportional relationship depends upon the value of alpha. What is the value of alpha? And this path from 1 to, let this 2 be, let this be 0.1, let this be 0.2. Now this is under the assumption when correlation coefficient is equal to 1. This means, or in other words we can say, there is no covariance between asset 1 and asset 2. So the path will be, if covariance between R1 and R2, only two assets we are assuming, if this is equal to 0, then the path will be decided by 1, 2 line. Now if covariance between the return on the two assets R1 or R2 is not equal to 0, the path will not be a straight line. Path will not be a straight line like 1, 2. Rather it will be a, rather this will be a curve convex to like this. So the path will be inside the triangle A1 A1 2. Clear? This is because of this the covariance factor. So this covariance factor is there, the path will go like this, and the dotted line actually shows the weight will be negative, and this dotted line shows that there is short selling or shorting is taking place. So this is the path, diversification path, you can say. This is diversification path. Now why this path will be 1 2, this can be understood with the help of this one example of simple mathematical derivation. What is this, in which we'll be proving this the point of this intersection on the vertical axis, how this height is being determined, how this is being determined, what will be the value of this height. Clear? So the value of this height, suppose two assets are there and W1 I have only two, we have taken two assets where W1 is equal to 1 minus alpha and W2 is equal to alpha again. So what about the mean return R bar alpha? This is equal to W1 R1 bar plus W2 R2 bar, or this is equal to 1 minus alpha into R1 bar plus alpha into R2 bar. So what is this? The overall average return is a linear combination of alpha and, clear? So this is the, or in other words we can say this is the weighted average of return on asset 1 and return on asset 2. If the two assets are equally distributed, means if alpha is equal to 0.5, means 50% of the asset purchase in the portfolio, the 50% asset is that of asset 1 and 50% is that of asset 2. So the mean return will be exactly in between R1 bar and R2 bar. It will be in between these two. So this is the mean return. Let us talk about this variance of R. The variance of R, this will be expected value of R minus R bar, this whole square. This we have already calculated earlier, and this was equal to sigma Wi Wj sigma Ij. Ij is equal to 1 to n. The two assets are there. For two asset case, here we can write it down like this. If I is equal to j, then this can be written as W1 square sigma 1 square plus W1 W2 sigma 1 2 plus W2 W1 sigma 2 1 plus W2 square sigma 2 square. Since covariances are symmetric in nature, covariance क्या है? They are symmetric. In that situation, sigma 1 2 is equal to sigma 2 1. The same equation for variance of R can be written as w1 square sigma 1 square plus twice w1 w2 sigma 1 2 plus w2 square sigma 2 square. This is the variance of R. Now, what about this standard deviation or sigma R? This will be a square root of this. What about standard deviation of R? We denote it by sigma R, because variance we denote by sigma square. So the sigma R will be equal to under root w1 square sigma 1 square plus twice w1 w2 sigma 1 2 w2 square sigma 2 square. Oh, we have already defined a term, the correlation coefficient denoted by rho. The correlation coefficient between 1, 2, this is equal to sigma 1, 2 upon sigma 1 into sigma 2. Covariance between asset 1 and asset 2. The correlation coefficient between asset 1 and asset 2. This is equal to covariance between 1 and 2 divided by a standard deviation of 1 multiplied by a standard deviation of 2. So from here you can find sigma 1 2, this is equal to rho 1 2 into sigma 1 into sigma 2. We shall substitute this value over here and try to get this one. So w1 square sigma 1 square plus twice w1 w2 rho 1 2 sigma 1 sigma 2 plus w2 square sigma 2 square. Now we replace this w1 by 1 minus alpha and w2 by alpha. So this is equal to 1 minus alpha square sigma 1 square plus twice into 1 minus alpha w2 alpha rho 1 2 sigma 1 sigma 2 plus alpha square rho 2 square. So this we can write down. With the help of this equation, we are in a position to find out the upper bound and lower bound values for this sigma s r, the upper and lower bound for this sigma. So the upper bound will be achieved when we assume the upper bound will be achieved when we assume that rho is equal to 1, and the lower bound will be achieved when we assume rho is equal to minus 1. So let us take first rho is equal to 1. Then sigma r can be written as 1 minus alpha square sigma 1 square plus twice 1 minus alpha into alpha sigma 1 sigma 2. This rho 1 2, rho means rho 1 2. This is rho 1 2. This is rho 1 2 plus alpha square sigma 2 square. So this is equal to, we take this and this we can write down 1 minus alpha sigma 1 plus alpha sigma 2 whole square. This is a plus b whole square, a square plus 2ab plus b square. So this can be written as sigma r is equal to 1 minus alpha into sigma 1 plus alpha into sigma 2. This is upper bound u for sigma. So what do we find? The upper bound for sigma is equal to this, and the mean of return is also equal is equal to this. So mean as well as sigma, they are linear combinations of alpha, or what you can say that mean rate of return is weighted average of individual rate of return and standard deviation for the asset as a whole. This is weighted average of the standard deviation of assets individual assets. Clear? So this is the linear combination of these two, and it is on the basis of this that we are in a position to say that R will movement of R bar and sigma will move proportionally, and it will be in the forward direction. You can see this diagram. You move here through a straight line because this R as well as sigma is a linear combination of alpha depending upon the value of alpha. If you are at this point, total investment is being made in asset 1. In this situation, alpha is equal to 0. At this point, total investment is being done in asset 2. So here alpha is equal to 1. Clear? In between we have like this, because R bar as well as sigma, they both are linear combination of alpha. 1 alpha. Let us talk about this lower bound when rho is equal to minus 1. If we talk about the lower bound, so sigma R lower boundary, so sigma R is equal to under root 1 minus alpha sigma 1 minus alpha sigma 1 plus alpha sigma 2 whole is minus alpha sigma 2 if rho 1 2 is equal to rho which is equal to minus 1. So this value we can write down like this: 1 minus alpha sigma 1 minus alpha sigma 2 within this boundary. So this is within this boundary. If alpha is small, then this sigma R, this will be 1 minus alpha positive minus alpha sigma 2. If alpha is large, then the sign will change, and this can be written as sigma R, this will be equal to alpha sigma 2 minus 1 minus sigma alpha 1. And this turning point will take place, the turning point will take place between this at alpha is equal to sigma 1 divided by sigma 1 plus sigma 2. It is only when alpha is equal to this much or greater than this much that we get this situation, or we get this position. So the sign is being reversed beyond this limit. The sign gets, this is, we are talking about the lower bound, reversed. The sign get reversed. So this is all about your today's lecture, where I've tried to look into the mean and the variance, mean, and all these things. We have tried to look into this. So the risk factor, Markov, the Markowitz diagram for diversification path, the diagram, and the diversification path will be somewhere. Then we can say it is because of the covariance factor. The covariance factor, that path will not be like 1 2, rather curve inside the triangle, inside the triangle. Thank you very much. This is all about today's lecture.